welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am from Department of Computer Science, Aryabhat College, University of Delhi. So presently we are going through our series of operating system concepts, and the topic which we are currently onto is about the process synchronization. So we have seen the concepts of threads, and in previous couple of lectures we have started with process synchronization, and we have seen that what is process synchronization, what is its need, and how can we implement the synchronization of various processes. So our today's lecture is focused on the critical section problem and its solution. So we have seen that critical section problem is one of the very important problem when we talk about or it is one of the very important concept when we talk about process synchronization. So with a quick recap of this critical section problem, which we have already covered in our previous lectures, we will be moving forward. So critical section problem. So critical section problem says basically the term critical section is a part of code that can only be accessed by a single process at any moment. Not more than any one process can be allowed to access the critical section. This is something which is related to having the right access of a file or any access of a shared resource which can be taken one at a time. So that's the problem is known as critical section problem. Basically a critical section is some part of code which is going to be accessed by a single process at one point of time. So now what happens when a lot of programs want to access and change a single shared data? Only one process will be allowed to do so at any given moment, while other processes will have to wait until the data or until the resource is free to be used. So for example, we have understood this critical section problem with the help of a we can say an account in which one process is trying to deposit an amount and another process is trying to withdraw an amount. So this amount or the amount of the account is something which should be accessed by one process at one point of time. So in Linux or in Unix, how are we going to handle these this section of code? So there are basically two system calls. One is the wait function, or you can say wait, which is going to handle the entry into the critical section, and another one is the signal function which is going to handle the exit from the critical section. So in order to kind of implement the entry and exit into the critical section for a particular problem, we have two functions. One is wait and another one is signal. Now if we talk about synchronization or any strategy which is there to help us in synchronization of various processes, we need to understand what is the requirement of synchronization. So there are basically three requirements of synchronization, and we have already seen details of this. So I'll be quickly going through these requirements. So first is mutual exclusion. So mutual exclusion as the kind of we are seeing into critical section process, only critical section problem, that only one process in the critical section is allowed to access that particular amount of that particular code or that particular data. So only one process can enter into the critical section, because critical section is something which is we can say taking the program or taking the job into that particular section which is a mutually exclusive section. So here there has to be a mutual exclusion. Then we have the next requirement of synchronization, which is process. So process which progress. So progress is the processes which are not executing in their remainder section. So we have seen in the earlier lectures that there is an entry section, then there is a critical section, then there is an exit section. and the remainder section. So who is going to enter in the critical section next? For example, we have many jobs or many processes which are trying to get into the critical section, then there has to be a decision on the basis of some factors that who is going to enter in this critical section. So all those processes which are not executing in their remainder section, so either they are in their entry section or in the exit section, they can participate in deciding which will enter in the critical section next. That is known as progress. And the third requirement is the no starvation policy. So no starvation, as the name indicates, every process which is looking for the critical section must be allowed to enter into the critical section, and a bound must exist on the number of times that other processes are allowed to enter their critical section before making the request for any critical any process in order to allow into its critical section. So for example, we have, let's process I is trying to get into the critical section and has already given its request. So there will be kind of a bounded waiting thing. So bounded waiting says there is a bound on the maximum number of times that the other processes before this ith process are allowed to enter their critical section. So that specifically means that wait for any process in order to access its critical section should not be endless, should not be unlimited. So there has to be a bounded waiting, and when there has to be a bounded waiting, it will automatically ensure the policy of no starvation. If there is no bound on the waiting, that means the waiting for entering into the critical section is going to be unbounded or limitless. There can be there we will be having starvation of processes. That means processes are starving in order to get entry into their critical section. So we have to have mutual exclusion. That means only one is allowed to enter into the critical section. Then there has to be some progress. That means the processes which are not in the remainder section which will decide that who is going to go next, and there should be the policy of no starvation as well. So these are the requirements of synchronization. And when we talk about the understanding of critical section problem, we have also seen the requirement of synchronization. Now let us try to understand what are the solutions available to this critical section problem. So the solutions available to this critical section problems could be in two categories. One is the software based solution and another one is the hardware based solution. So today in this lecture we are going to look for classical software based solution or software based solution. So within the category of software based solution, we have one solution or one algorithm basically, which is known as Peterson solution. It's a very classically acclaimed software based solution for this critical section problem. Now what is the what are the disadvantages, what are the advantages of this Peterson's algorithm, and how it is going to implement? So let's try to look into this. So as I have told you, this is a software based solution, but this is a solution which is having constraints practically, or I can say it is a practically constrained solution. Why? Because this is based only on the two processes and only on the two processes. So this is going to work with only two processes, and also we can say it is an algorithmic description of solving the critical problem. So basically if we talk about these two things, one is the practically constrained solution because it is considering only the two jobs. Looking at the systems nowadays, it is hard to have only two jobs for such a situation. There can be multiple, there can be many jobs. So yes, it is a practically constrained solution, and it contains only the algorithmic description of solving that critical section problem. Within this algorithmic description, it also contains some instructions which are for machine to understand, which are basically machine language instructions such as load and store, and these are some instructions which which don't guarantee that this solution is going to work correctly on modern architecture, because this load and store may vary from architecture to architecture. So basically we can say this is slightly dependent on machine language, that's another constraints. But this is going to deal with some of the complexities involved in designing softwares that address the requirements of mutual exclusion, progress and bounded weighting. This algorithmic solution is going to give us a clear idea about the complexities which are involved in designing the software, and also how to address the requirement of mutual exclusion, progress and bounded weighting, which are the requirements of synchronization. This solution is going to give us at least a kind of view about that. So when we talk about the Peterson solutions, we have as I have told you that this is something which is going to be restricted to two processes only, and there is going to be an alternate execution between their critical section and remainder section. So one is in the critical section, another one is in the remainder section, and so on and so forth. Now let us say these processes are numbered as P0 and P1, or for example we can say Pi and Pj. So when we are talking about the two processes Pi and Pj, and these are the two processes that are executing in alternate mode between critical section and remainder. So we are going to use j equals to 1 minus I. So for convenience we are presenting Pi and we need to denote Pj, which is where j is equals to 1 minus I, and here we are talking about only two processes. So that's the biggest restriction here. Now how your critical section problem is solved using the Peterson solution. Let's see an algorithm first. I'll go through this algorithm and then I'll explain it. So the algorithm, as you can see on the screen, says do flag of I is equals to true. So I here is the job, then turn is equals to j, while flag of j and turn equals to j, critical section entry, and then flag of I is equals to false, and then there is a remainder section while true. So this loop will go on and on. So what is actually happening in this do while loop? So basically there are two variables which are used by the processes, and these variables are shared. These variables are there in order to ensure that only one variable, only one process is allowed to enter into the critical section. Now what are these shared variables? One is a flag, which is a Boolean array. So basically a flag which is initiated to false first, and this flag array is representing which process is ready to enter into the critical solution. So for example, both the processes are ready, then in that situation the flag will be true for both. The next is the variable turn, which is of type integer. So this integer turn is a variable of type integer, which is there to indicate the process number which is ready to enter the critical section. So for example, turn equals to I, then the process Pi is allowed to execute into its critical section. So we have two variables which are shared between the two processes which are participating in the solution of this Peterson algorithm. So one is the Boolean array flag, which is initialized to false initially, which indicates which process wants to enter into the critical solution. So the process which is looking for entry into the critical solution, for that particular process flag will become true. Another is the integer turn, which represents the process number which is ready to enter into the critical section. So here you can see we have a flag array, and in this flag array we have n processes, and for this n processes, and I have told you that this is a Boolean array, and so for n processes we have 1 to n, the size of the array will be n, and here you can see that there are two values in which the value of the element of array is true, and these values are nothing but 1 and 4. So basically process number 1 and process number 4 are ready to enter into the critical section. So the variable which is turn is going to indicate whose turn it is to enter the critical section, and the flag array is used to indicate if a process is ready to enter its critical section. So here I am repeating this. Please listen it very carefully, that the variable turn indicates whose turn it is to enter the critical section according to the decision taken, and the flag array, which is an array of Boolean values, and it's an array of 2 elements of size 2 if we are talking about Peterson solutions, because the only 2 processes can participate here. So this flag array is used to indicate if a process is ready to enter its critical section. So how many processes are ready to enter its critical section? There could be 2 or there could be n. If we talk out of this Peterson solution, there can be n processes which are ready to enter its critical section, but it is the variable turn who is going to regulate that whose turn it is in order to enter into the critical section, or which process wants to enter into the critical section. So for example, flag of I is true. So this value indicates that the process Pi is ready to enter into its critical section, or let's say flag of J is true. That means jth process is ready to enter into its critical section. So now in order to enter into the critical section, what a process needs to do? Any process first needs to set its flag to be true. That means it has to kind of indicate its desire or indicates its preparation that yes, I am ready to get into the critical section. So that is indicated through the value of flag, and then it is going to set the value of turn to the index. So for example, if I am talking about the process Pi, so process Pi first sets flag I to be true and then sets the turn to the value j. By setting the turn to the value j, this process is asserting that if other process wishes to enter in the critical section, it can do so. So now it's the turn of the jth process to enter into the critical section, but flag I indicates that process I is also we can say ready to enter into the critical section. Now is there any possibility that both processes can enter into the critical section at same point of time? Is it we can say is it a possible scenario? So for that we need to look for this algorithm into once again. Now as we have understood the value or the intention behind this Boolean array flag and the integer variable j, we will have a different perspective here. So here we are in a do while loop, which is kind of an infinite thing. While true it is going till. So flag of I is equals to true. That means ith process is ready to get into its critical section, and turn equals to j. That means it is the jth process which is going to get into the critical section, and these value of these two variables will hold same while your flag of j and turn equals to j. So while your turn is equals to j and flag of j is set in the sense that j is also ready to get into the critical section, that means all preparations have been done, and also the turn has been allocated to j by saying turn equals to j. So while your turn is with j and while j is ready to be into or get into the critical section by indicating a set value of flag j, these two variable values will hold as it is. And then there is a critical section in which your jth process or process pj is going to work, because it is the turn of pj, and then after execution of its critical section we have flag is equals to false, and then we have a remainder section. So with this thing we have situations that how we are going to deal with. So in order to enter into the critical section, the process Pi first sets the flag I to be true, that we have seen in the code, and then sets the turn to the value j, thereby asserting that if the other process wishes to enter the critical section, it can do so. Now what will happen, I was discussing that what will happen if both the processes try to enter at the same time. Both will try to set the variable turn at the same time. That means there are two processes which are saying turn is equals to I, or maybe turn is equals to j. But is it possible to assign the value in a variable or two values in a single variable at the same time? No, it is not possible, and the eventual value because one will be kind of overwritten immediately if other is going to be written onto it. So only one of these assignments will last. So either turn equals to I is going to last, or it is turn equals to j which is going to hold. So the other will occur but will be overwritten immediately, because there is a single variable and we cannot put in two values into those variables. Then the eventual value of turn determines which of which processes is allowed to enter into the critical section first. So it is the final value of turn which is going to decide that which of these processes, whether I or j, is allowed to enter into its critical section first. Now with this thing, till this point what we have covered, we have seen what is the critical section problem, what is the synchronization in critical section, then we have why this synchronization is required, and what is this critical section problem, how this is we can say attached to, or how this is attached to the process synchronization thing. Then we have seen what are the requirements for synchronization. So we have seen there are three requirements of synchronization. One is mutual exclusion, another one is progress, and the third one is no starvation, that is bounded waiting. And all these three solutions, or all these three requirements should be should stand completed if we are looking for any solution towards the critical section problem. Then we have seen that there are kind of two categories of solutions to the critical section problem. One is the software based and another one is the hardware based. And then we have seen then we have started with the software based solution, and within the software based solution we have one very classical solution, and that is known as Peterson solution. We have started studying that Peterson solution with the condition or with the restriction that this solution is only going to hold for two two processes, and that's why we have claimed that this is just an kind of an algorithm in order to visualize what is happening what is happening inside the algorithm and how all these things will be managed. This will not be used or claimed practically because it is having constraints such as it is based only on the two processes, and then so on and so forth. And then we have also seen that how this Peterson solution is going to ensure the solution to the problem of synchronization, at least in case of two processes. So there are two variables, one is the turn and which is of type integer, and another one is an array which is a array named as flag, and that is a Boolean array. So for those who are having the value of flag as true, that means they are ready to get into the critical section, while one who is going into the critical section will be a process whose turn is this. So that means if turn is equals to I will be going to get into the your critical section, and if turn equals to j, then the process j is going to be entered into the critical section, and it is not possible that this variable turn is going to have two values. So in this way your Peterson solution is ensuring the solution, Peterson algorithm is ensuring the solution to synchronization. Now we have seen what is the solution by setting off these two variables and allowing only one to enter into the critical section. We also need to prove that this solution which is being proposed as Peterson algorithm is correct. Now what we need to do in order to prove that the solution is correct, we need to show all those requirements of synchronization which are mutual exclusion, then we have progress requirement, and then the bounded weighting. All these three should be preserved. So mutual exclusion is going to be preserved while your progress requirement is satisfied and the bounded weighting requirement is going to met. All these three conditions are standing are holding for your Peterson solution. That is something which we will be exploring in our upcoming lecture. So here is a list of references which is being used for the preparation of this lecture. Hope you had a fruitful learning. Thank you.